I've been sick for the past 3 days, so I'm sorry if my voice cracks like a 13-year-old. But like Erica said, my name is Elias Picazo, and this summer I've been working in Professor Zakarian's lab with my mentor, Aaron Herman, under UC Leeds. So today I'll give a presentation on my project on a diastereoselective trifluoromethylation. I'm sure you've all seen a periodic table before. It's just every time.
Check the do not show this list.
Oh, I'm the last one. But I'm sure you've all seen the periodic table. It's a clean, tabulated method of showing the elements. And I'd like to highlight fluorine. It's located on the upper right-hand corner, zoomed in up here, because I've been working with it this summer and it has very unique characteristics. For example, it bonds very strongly with carbon. If you compare it to another halogen like chlorine, you can see that it takes more energy to break the bond. And when you add another fluorine atom, it actually makes the carbon-fluorine bond stronger rather than weaker. And not only does it make its bond with carbon stronger, it also makes other bonds with carbon stronger, like hydrogen, shown with these two. Another characteristic of fluorine is that it's very small. It's the second smallest on the periodic table, next to hydrogen. So you can see that it bonds really closely to carbon, and it has a very small atomic radius. The final property of fluorine that I'd like to share with you guys is the electronegativity. It's electrostatic characteristics. If you look at the image on the left, you see that all of the electron density lies within the middle of the circle in this benzene ring. But when you fluorinate the ring, you see that, well, I have the colors down here. So yeah, the electron density is in the middle here, and then with the fluorine, you see that the fluorine draws the electrons towards itself. And so because of these characteristics and more, fluorinated compounds have been shown to be beneficial in a lot of areas. So like in agriculture, you see the fluorine atoms in this molecule make this molecule like an effective insecticide. And the molecule on the right is known as Prozac, so it's an antidepressant drug. And like people have said before me, there are organic compounds that can be used for semiconductors, which are useful in technology and LCD displays. And to expand a little bit more on pharmaceuticals, I have this chart, and these are IC50. It illustrates IC50s, and so Taxol is an anti-cancer drug, and these two are derivatives of Taxol. And the lower the number, the more effective the drug is, because it means that it took less concentration of that molecule to kill off 50% of the cancer cells. And so you can see by this chart that the bottom of the three was most effective. And the main difference between these three molecules is that the last one has a trifluoromethyl group down highlighted on the bottom. And this kind of ties into what I was doing this summer, because I'm working on trifluoromethylations, and as you can see, all these wedges and dashed lines, they show stereochemistry, which means how things bond in a molecule, like orientation in space. And so previously, before I was in the Zakarian group, they were working with perfluoroalkylations, which are just longer chains of carbon saturated with fluorine. And they found that these reactions gave moderate yields and good stereo control. So 98% of one shape over the other. So 98 to 2, 96 to 4. And you can see that the weakest one was the trifluoromethyl group. And the thought behind this is that the trifluoromethyl group is so small that it can attack from one side or the other. So my project this summer was changing the auxiliary. You can see the main difference was here highlighted. I try to make it more bulky in this position, so I added steric so bulk, so that when it tried to attach from one way, it wouldn't be able to, so it had to go around. and go to the back. And my project was to figure out the diastereotopic ratio of the two compounds. I started with L-valine. That's the main difference between their project because they started with phenylalanine. And I formed this ester here and then treated it with Bach to form this carbamate, which is just the name of this group of compound, or this group of elements here. And once I got to that part of the project, I took it in two different directions. At the Grignard step, one was methyl and one was ethyl. And I did this to see if the stability would change, so that when I got the final auxiliary, you can see the difference was here. You can see the methyl and the ethyl groups here. Ethyl is just 2 carbons and methyl is 1. Once I got the auxiliary, I was able to acylate it, and you can see the yields were relatively high for this reaction. And once I acylated it, I got to the actual trifluoromethylation, and the results were actually really exciting because not only did the ratio go up from 90% to 98%, but the yield also increased by 15%. So it was really promising, and the yield for the methyl group was higher than the ethyl group. And so I have an NMR showing you this compound here. Like Lindsay said, NMR is used to characterize a molecule, and so every hydrogen on a molecule has its own peak or set of peaks. And I'd like to highlight 2 of them specifically because this trifluoromethyl group, before I trifluoromethylated it, these peaks were a lot more downfield, but since I said earlier fluorine is very electronegative, it shifted the peaks more to a higher ppm, so more upfield. And I highlighted these peaks because before, if you have a different diastereomer, so it's different in space, it'll be influenced by different surroundings and you'll have a different set of peaks. But as you can see with this NMR, the peaks are very clean, implying that there's an overwhelming amount of one diastereomer over in the unit. And so now that we've seen that the reaction works well, we can see the scope of the reaction and see the limitations of it too. So we can do multiple things like lower the amount of time we let it react, or change the amount of catalytic loading, or lower the temperature, because these are run at 45 degrees Celsius. And then we can also explore different substrates like they did previously. They had different groups, and so we're looking forward to testing these because they were problematic when we were doing the phenylalanine group, or the benzyl group down here. And we can also try different things like the longer chains and the perfluoro alkylations and see if it's also giving higher yields for those. So I'd like to thank you guys for listening, first of all, and also thank my professor for all the help, and my mentor, Aaron Herman, sitting in the back. Everyone look at him. And everyone else in the group that was helping me all the time. Like, if I had a question, they were always willing to help me out. And Erica, thank you very much for advising me throughout the program. Tyler for listening to my presentations and helping me out, and Professor for the organic aspect of the presentations. And everyone else, who's Maria, for helping us with everything, and then the food. Thank you.